So in this section 2.4, what we're going to do is we're going to explore limits in greater detail. In the previous section, we did a plug and chug. We plugged in a value for x, and if we got a value back, we were done. If we plugged in a value and we got an indeterminate form, such as 0 over 0, that told us we had to do something more, such as algebra, or maybe coming in from the left and coming in from the right. And then the last example we did in the previous section was the squeeze theorem. So that's where you get a form, such as an indeterminate form. You don't know how to evaluate it, so you kind of squeeze your function in between two other functions that have the same limit. In this section, we're going to look at something that happens sometimes when you take the limit. Sometimes it could happen that you go to negative or positive infinity. So in this first graph, let's just look at what happens as we approach 0. As we come in from the left and our x values get closer and closer to 0, what's happening to the y values is they're going up to positive infinity. So I would write the limit as x approaches 0 from the left. Let's call this function f of x is equal to positive infinity. Whenever a limit is equal to positive or negative infinity, technically it does not exist, because for a limit to exist, we have to approach a value. Infinity is not a value, it's just a concept. We have to approach a value, and we have to be able to get as close as we wish. We cannot get as close as we wish to infinity. So although technically infinity means the limit does not exist, we still write infinity. The reason why is because it tells us a lot about that graph. Notice that if your function or your graph goes up, what you end up with is you end up with a vertical asymptote. Okay? So that's from algebra. So at 0, what we have is a vertical asymptote. What happens as we come in from the right? So as our x's get closer and closer to 0 from the right, our graph is going up to positive infinity. So we would write the limit as x goes to 0 from the right of our function f of x is equal to positive infinity. Again, with the understanding that positive infinity technically means the limit does not exist. So notice that when I come in from the left and the right, I get the same limit. I get infinity. So we can say that the limit as x approaches 0 of our function f of x is equal to infinity. Whenever you get infinity or negative infinity, that tells you it's a vertical asymptote. Let's look at the next graph. As we approach 0 from the left, what happens is the graph goes down to negative infinity. So I would write the limit as x approaches 0 from the left. I'll call this function g of x is equal to negative infinity. And as we come in towards 0 from the right, our graph goes up as we get closer and closer to 0. So we write the limit as x goes to 0 from the right of x is equal to positive infinity. So now as I come in from the left and the right, I say I have different limits. So we say the limit as x goes to 0 of x does not exist. So DNE for does not exist. So whether you come in from the left or the right, if you do get a negative or a positive infinity, that tells you that you're going to have a vertical asymptote. Let's look at some definitions. So the definition of an infinite limit has all the stuff we had before. You have your f, it's defined for x near a, except possibly at a, so the usual limit stuff. So if f of x grows arbitrarily large for x's sufficiently close to a, then that would be our limit. It would be positive infinity. And this is how we would write it. The limit as x goes to a of f of x is equal to positive infinity. Now, if f of x is negative and grows arbitrarily large in magnitude, and the reason why that's there is because you can't get large negative values, right? Negative by definition means it's getting smaller and smaller. So the magnitude just means absolute value. So if the absolute values are getting larger and larger and larger, but the values themselves are negative, then we write the limit as x approaches a of f of x is equal to negative infinity. Okay? Keeping in mind that in both cases, the limit does not exist. Okay? However, we keep it as positive and negative infinity because it tells us a lot about our graph. One-sided limits, the same as before. We're looking at f defined for all x near a, x greater than a. If x grows arbitrarily large, then we would go ahead and write the limit as x approaches a from the right is positive infinity. And then we have some similar definitions for approaching from the right and having it be equal to negative infinity, approaching from the left, having it equal positive infinity, approaching from the left, and it equals negative infinity. So this is the important stuff. Vertical asymptote. If the limit as f approaches a of f of x is either negative or positive infinity, and it doesn't matter if you approach from both sides, if you come in from the right, or if you come in from the left. If you come in from one or both sides and you get either a negative or a positive infinity, that tells you that what you have is a vertical asymptote. So if you were to write the vertical asymptote, remember it's a vertical line, so it's going to be x equal to a. It's going to be the equation of a vertical line. Let's go to the next slide and do some examples. Okay. In example 1, it says sketch the graph of a function that satisfies the given conditions. Include any vertical asymptotes. Wonderful. So first I'm going to draw myself a coordinate system. Okay. And then I'm going to look at my conditions. Well, I always start with what I know. F of 0 is equal to 1. So when x is equal to 0, I have a, oops, let me make a little line there. I think I'm going to use green. I have a y value of 1. So it's going to pass through the point 0, 1. There are no x-intercepts. So whatever graph I graph can't cross over the x-axis. I know that the limit as x approaches 3 from the left is going to be a positive infinity. So if I go 1, 2, 3, and since the limit is a positive infinity, what that tells me is that I'm going to have this vertical asymptote, which is x equal to 3. As I come in from the, I want blue. I'm changing my colors. I want the blue. So as I come in from the left of 3, this graph is supposed to go up to positive infinity. Okay? So I got the point 0, 1. I have the limit as I come in and approach 3 from the right, the limit's going to be negative infinity. So I'm going to come in and I'm going to approach 3 from the right, and I'm going to go down. Oops, I hate it when I do that. And I'm going to go down to negative infinity. So I could keep having the function go off in the other direction, but I have to be careful because there's no x-intercepts. I don't want to cross over the x-axis. But I can always just have it start some random point. So I met all the conditions. As I come in from the left, it's going to positive infinity. From the right, we're going to negative infinity. It passes through the point 0, 1, and there are no x-intercepts. So remember, this is not unique. Whenever you're sketching a graph that meets conditions, there could be infinitely many graphs that meet those conditions. In example 2, we want to determine this limit. The limit as x goes to 3 of 1 over x minus 3. So if I were to plug and chug, I would get 1 over 0. That is not an indeterminate form. 0 over 0 is, but 1 over 0 is not an indeterminate form. What that tells me is there's probably going to be a vertical asymptote. I just have to figure out if it's a negative or a positive infinity. So what we're going to do is we're going to make a table. However, remember what I said. We typically don't use tables and graphs to evaluate limits, but I'm going to make a table so you can see what's happening here. As I approach 3 from the right, so in my table I'm looking at 3.1, 3.01, and so on. What is my f of x? So at 3.1, this is going to be 1 over 0.1, so it's going to be 10. At 3.01, if I plug that in for x, I get 1 over 0.01, which is 100. And then I'll get 1,000, 10,000, and 100,000. So that tells me as I approach 3 from the right, this is going to be equal to a positive infinity because the numbers are getting larger and larger and larger as I get closer and closer and closer to 3 from the right. If I look at part B, put in 2.9 for x, I get 1 over negative 0.1, so that's going to be a negative 10. If I put in 2.99 for x, I get 1 over 2.99 minus 3 would be a negative, right? 0.01, so it's going to be a negative 100. And then a negative 1,000, negative 10,000, and a negative 100,000. So you can see that as I get closer and closer to 3 from the left, my values are getting larger in magnitude, right? 10, 100, 1,000, 10,000, but they're negative values. So coming from the left, we're approaching negative infinity. We were supposed to be looking at what happens to the limit as we approach 3. So as we came in from the right, it was positive infinity, left was negative infinity. So I can conclude that the limit as x approaches 3 of 1 over x minus 3 does not exist. So I said that we don't usually use tables. So what happens if we don't have a table? Well, let's go back up and look at the limit as x approaches 3 from the right of 1 over x minus 3. Normally we plug and chug, so this is going to be 1 over 0, which is not indeterminate. What that tells me is that this function is undefined at 3. So what happens as it approaches 3? So it's either going to be a negative or a positive infinity. Since we're looking at x values that are larger than 3, that my x values are larger than 3, my denominator is always going to be positive. So I'm going to put a plus next to this 0 to indicate that my denominator is getting closer and closer to 0, but with positive values. So think about this. We have a fraction, positive over positive. So what that tells me is this is going to be equal to a positive infinity. Okay, let's try the other side. So if we take the limit as x approaches 3 from the left of 1 over x minus 3, that's going to be equal to 1 over 0. Okay? So that tells me that my function is undefined at 3. Tells me that I'm going to have a vertical asymptote. Is it going to approach positive or negative infinity? Well, if I look at these x values, I'm putting in numbers that are smaller than 3. So that means my denominator is going to be negative. So I have a positive number over a negative number. Positive over negative is negative. That tells me that this is going to be approaching negative infinity, which is what my table gave me. At a negative infinity as I came in from the left and a positive infinity as I came in from the right. So that's actually algebraically and using logic how we would compute to figure out if we had a negative or a positive infinity. I'd like to look at the property at the top of the next page. It says, for any fraction of the form a over b, so a and b are just real numbers. As b gets smaller and smaller and approaches 0, the whole fraction a over b is going to approach either a positive or a negative infinity. And here we're assuming that our a is not equal to 0, because otherwise it would be an indeterminate form. So a is just some fixed real number, like 1. And b is going to be some number that keeps changing and getting smaller and smaller. So let's say b is 1. Okay. Well, what happens as I go to 0.1 and to 0.01 and to 0.001 and to 0.0001? So as the b values get smaller and smaller, as long as the numerator remains fixed, notice that this is 1, 10, 100, 1,000, 10,000, and so on. So this is approaching positive infinity. If the denominator gets smaller and smaller and smaller and the numerator remains fixed, then the fraction is going to approach negative or positive infinity. And that's what we're going to use when we evaluate it. Just determine whether your denominator is negative or positive, and then you'll either have a negative or a positive infinity. So we were talking about vertical asymptotes. From algebra, how we found vertical asymptotes was pretty much we would set our denominators equal to 0 and figure out what x values made the denominator equal to 0, and those would be our vertical asymptotes. So the way that we find vertical asymptotes is we take our function and we make sure everything is factored on the top and bottom. So I can factor out an x in the numerator. And in the bottom, that's a trinomial that would factor as x minus 3, x plus 1. So whatever makes the denominator 0 is supposed to be a possible vertical asymptote. But remember, you always have to make sure you factor and cancel first before you determine what your vertical asymptotes are. A lot of times people forget that. they'll just go straight to the denominator. So I'll do this two ways. I'm going to first find possible vertical asymptotes by factoring and canceling, and then looking at the x values that make my denominator 0. So the x value that makes my denominator 0 is -1. So x equal to -1 is going to be a possible vertical asymptote. So I'm going to put VA for vertical asymptote. And then what I'm going to do is I'm going to use calculus to verify that it is a vertical asymptote. So the calculus part is taking the limit as we approach -1 from either the left or right. It doesn't really matter. If we get a negative or a positive infinity, then it's a vertical asymptote. Once I get a negative or positive infinity coming in from one side, I'm done. I don't have to come in from both sides. So let me take the limit. As x approaches -1, and I'll come in from the right. So I'm going to use the simplified x over x plus 1, right, because I've factored and canceled. If I put in -1 for x, so plug and chug, I get a -1 over 0. That is not an indeterminate form. That tells me I have a vertical asymptote. Am I approaching negative or positive infinity? Well, I'm looking at numbers that are larger than -1, so my denominator is going to be positive. So negative over positive would mean negative infinity. All right, so I've just used calculus to show that I have a vertical asymptote, but I have to make a conclusion. Remember, I wasn't supposed to just compute the limit. What I was supposed to do is verify that x equal to -1 is a vertical asymptote. Taking the limit is the verification. So once I take the limit, I can conclude, so I'm going to just write thus. There is a vertical asymptote at x equal to -1. And that's it. Use algebra to find possible vertical asymptotes. Use calculus to verify the vertical asymptotes. So let's just say that you forgot to cancel, and you had f of x equal to x squared minus 3x over x squared minus 2x minus 3. And you remembered from algebra that all you had to do was take that denominator, x squared minus 2x minus 3, and figure out what x values make it equal to 0. So you would factor and get x minus 3, x plus 1 equal to 0. So x equal to 3 and x equal to -1 are possible vertical asymptotes. To show that they are vertical asymptotes, I have to show that when I come in from either the left or the right, I get a negative or positive infinity for my limit. So now we already verified that x equals to -1 is a vertical asymptote. So this is already verified. So let's work on x is equal to 3. If I take the limit as x approaches 3 from the right of my function x squared minus 3x over x squared minus 2x minus 3, what I get is I get 0 over 0. I get the indeterminate form, which tells me I need to do something more. And that something more is factor and see if anything cancels. So we would take the limit as x goes to 3 from the right of x over x minus 3 all over x minus 3, x plus 1. And then after canceling the x minus 3, we get the limit as x goes to 3 from the right of x over x plus 1. So when I plug in 3, I get 3 over 4. So I did not get positive or negative infinity. And I expected that I wouldn't, because I know from factoring and canceling that x equals to 3 is actually not a vertical asymptote. If you were to graph it, there would just be a hole in the graph at x is equal to 3. So I came in from one side, and I did not get negative infinity, I did not get positive infinity. So all that tells me is when I come in from the right, it's not a vertical asymptote. It could be that there's a vertical asymptote coming in from the left. So if I were to check the limit as x goes to 3 from the left of my x squared minus 3x over x squared minus 2x minus 3, again I would get 0 over 0, the indeterminate form. So clearly I'm going to go ahead and factor and cancel. So after I factor and cancel, since it's the exact same operation I had on the other side, I'm just going to go to x over x plus 1. And then when I plug in 3, I get 3 over 4. So we came in from the right, we did not get negative or positive infinity. We came in from the left, we did not get negative or positive infinity. So that tells me that there's no vertical asymptote at x is equal to 3. So even if you forget to factor and cancel, you would still verify all your possible vertical asymptotes, and if it's not a vertical asymptote, it's just a hole in the graph, you won't get negative or positive infinity. So what we're going to do now is we're just going to power out a few examples of limits, and then that's it for this section. Okay? So the goal in this section is just to evaluate limits where you get a number over 0 and determine whether it's a negative or positive infinity. And then the other part of this section was to verify that we had vertical asymptotes by using calculus, by taking the limit. In example 3a, I'm taking the limit as x goes to 4 from the right of x minus 5 over square root of x minus 2. So when I plug and chug, when I plug in 4, I get 4 minus 5 is negative 1 over the square root of 4, which would be 2 minus 2. That would be 0. So that tells me that it's going to be negative or positive infinity. I just have to determine if it's negative or positive. So as we approach 4 from the right, the square root of x is going to be larger than 2, so my denominator is going to be positive. So I have a negative over a positive, which tells me that this is going to be equal to negative infinity. I suggest not using a table, because this is where you get to really practice those critical thinking skills. However, you may use a table just to verify, but try it without the table and then verify with tables if you're more comfortable using tables. Let's look at part B. Again, I'm approaching 4, so if I just plug it in, I get negative 1 over 0. But since I'm approaching 4 with numbers that are smaller than 4, that means the square root of x is going to be smaller than 2. So my denominator is actually going to be negative. So since I have a negative over a negative, that's going to give me a positive infinity. C is an interesting example. If I plug in pi, I'm going to get pi over the sine of pi is 0. So pi over 0 tells me I'm probably going to have a vertical asymptote. Let's determine whether it's negative or positive infinity. So this is a little bit tricky. right? Because we're approaching pi from the right, so numbers larger than pi. So is sign going to be negative or positive? Let's go back to our unit circle and think about this. Let me draw my sad unit circle. So remember, this is 0, pi over 2, pi, and 3 pi over 2. So if I'm approaching pi from the right, I'm approaching in quadrant 3, which means that sign is negative because we're in quadrant 3. So going back to trig in our unit circle. So my denominator is going to be negative. So positive over negative tells me that this is going to be approaching negative infinity. All right. In D, the limit as x goes to 4. If I plug that in, I have a negative 3 over, if I put in 4, I get 16 minus 40 plus 24. So it's going to be 0. However, I have this parenthesis around my 0 and it's being squared. So I have an even exponent. So typically, if we get a number over 0, we have to come in from the left and right. Because on one side we could have a positive infinity, the other side we could have a negative infinity. So again, whenever you have a number over 0, if you're not told to, if you're just given a usual limit coming in from both sides, you're going to have to split it up from left and right. But in this case, I actually don't have to. Because think about this logically. Doesn't matter what those x values are. If I come in from the right, I'm going to get some number, but I'm squaring it, so it's going to be positive. If I come in from the left, number smaller than 4, I'm going to get some number, but I'm squaring it, so it's going to turn positive. So because I have an even exponent, it doesn't matter if I come in from the left or the right, this is always going to be equal to a negative over a positive, which would just give me negative infinity. So that would be a special case where you don't have to come in from the left and the right. That's not the case for E. If I plug in 1, this is going to be 5 over 0. And unfortunately, it's not raised to an even exponent. So I'm going to have to break this up and come in from the left and the right. So if I take the limit as x approaches 1 from the left of 5 over x to the third minus 1, and I plug that value in, plug in 1, I get 5 over 0. So now I need to determine whether that 0 is positive or negative. So I'm approaching 1 from the left, so numbers smaller than 1. What's going to happen is my denominator is actually going to be negative. Positive over negative is going to give me a negative infinity. When I come in from the right, so as x approaches 1 from the right, of 5 over x to the third minus 1, I get 5 over 0. Is it a negative or a positive? So numbers larger than 1 mean my denominator is going to be positive. Positive over positive is positive infinity. Okay, so what does this mean? Well, this means that my limit as x approaches 1 from the left and the right of 5 over x to the third minus 1 does not exist because I approached two different values, one negative infinity, one positive infinity. And that's it for this section 2.4.